Hello and welcome to the course. I consider this an advanced R programming course. However, we will start at the very beginning and build things up from there, but we'll move pretty quickly. So I see this as a course for someone who has done some R programming already and wants to dig down into the fundamentals and really learn how the language works, or someone who's done programming in a different language and wants to learn R as well. If you've never done any programming at all, this is probably not the right course for you. I would suggest our course Introduction to R Programming might be better. Okay, so let's jump into it. So one of the most important things to understand about a programming language is its data structures. And R has many different data structures. In this first set of videos, we're going to be talking about vectors. And there are two types of vectors: atomic vectors, which we'll talk about in this video. So this is what you think about as a vector normally when you think about a vector. And then we also have lists, which are more unstructured types of objects. And that will be the subject of the next video. Okay, so let's just throw in an example here. So I'm going to type here. Oh, by the way, I think the best way to get the most out of these videos is to follow along and type in the commands as you go. So I'm going to provide links to this script here. It'll be called atomicvectorsblank.r, and then it'll just have these comments in it. So I would follow along and type these in as you go, and you'll probably need to pause at some points to keep up. And then I'll also provide the full script with everything typed in, which will be the results of when we're done here. So I think it's probably best to get two screens somehow. So that could either be like a tablet in your computer, or if you can pull up YouTube on your television and have your computer next to it, that's probably the best way to do it. To have two screens where one you could be watching the video and another one you could be on your laptop in RStudio typing in commands. Okay, so that reminds me, we're in RStudio here. So you'll have to have this installed before you start learning. And that involves installing two things. One is installing R, which most likely you already have, and then installing RStudio, which is what's called an integrated development environment for R. So there's two separate things you have to install. But likely most of you already have R and RStudio installed because you've done a little bit of R programming already. Okay, so let's get back to atomic vectors. So I'm going to type something here. A is 1:20. So you see what's happening on this line is I'm using some R syntax to define the vector of integers between 1 and 20. And then I'm assigning that to a variable called A. And I am over here in a script called atomicvectors.r. This is a .r script. That just means it's a text file with R commands in it. Any line that starts with a £sign or hashtag is a comment. This won't be run. And then any line doesn't start with 1 will contain or should contain R code. Now I have it set up so that I have the maximum possible real estate for my R script over here, and then on the right side I have the R console over here. So you can go back and forth between these two. You may set it up slightly differently, but if you don't know how to do it, I would set it up this way. And you can follow through the menus here in Tools. You can go in Global Options and set things up how you like it. Okay, so here we're defining this object A, which is the vector of integers 1 through 20. And I think it's a good idea to get in the habit of using keyboard shortcuts. So you could run this line by taking your mouse and clicking Run. That will send this over to the console. And then you could click in the console and type A and it will print it out. So this just shows that that's the vector. And then you can click back over here and start working again. However, there's a faster way to do it. So I would the way I run things is I type Control Enter. That sends it over. And so I don't have to use the mouse. And then I can just keep typing here. So if I want to print out A, I'll just type A, hit Control Enter again. And my hands have never left the keyboard. So get used to using these keyboard shortcuts. There's a menu in here. If you go to keyboard shortcuts help, it should pull something like this up. So take a look through there's lots of them, but there's a few that we'll be using over and over again. One is Control Enter. Now it might be slightly different in your system, so you have to check the keyboard shortcuts. All right, next one I want to tell you is if on my system, if I do Control 2, that will move the cursor over to the console. So that's a quick way to go from the script to the console, and then Control 1 will go back. On a Mac, it's probably Command 1 or Command 2. You'll just have to look up what the right keyboard shortcut is. So Control Enter and then Control 1, 2 are keyboard shortcuts I use all the time. Okay, so this is vector, the numbers 1 through 20. This colon operator means I'm going to take each individual integer between 1 and 20 and put them in a vector. Okay, why is it called an atomic vector? The reason is that each element of the vector, so for example, the third element of this vector is 3, it's indivisible, meaning like it itself is not something that could be subset into something smaller. So that's where the atomic name comes from. Atomic vectors have the additional property that all of the elements of the vector are of the same type. So one of the important concepts in programming languages is to understand how types work. And there's a function in R that can tell you the type of the object. So type of A, Control Enter, tells me that this is a vector of integers. Now you can also get help. So here's our first instance where we're explicitly calling a function, the function type of, with argument A. If you want to get help on a function, you can go in the console and just type question mark and then the name of the function, and that will pull up a help file. So I'd encourage you to read through these things. This one's very short. The way this is set up is there's some information about at the top saying which function it is, which package it comes from, a short description, and then a longer description. Type of determines the R internal type or storage mode of any object. And this is how it's used. So there's usually a usage section that tells you how to call the function. And then if there's any arguments to the function, there'll be an arguments section which tells you what the thing is that you're putting in there. So you can basically put in any R object in here and you can get its type. Help functions, help files will also have a value section that tells you what the function returns. So this function returns a character string, and you can see that here. It returned the character string integer. Now we'll talk more about character strings in just a minute, because that's another type of variable. Okay, so let's run through some of the main types. So we've already seen integer. Let's do logical. So let's define a vector. B is true, false, false, true. Okay, so you see what we're doing here is I'm using a function called C. C stands for concatenate. And what C does is you put in values separated by commas, and the C function will concatenate them into a vector. So here is one way we created a vector with the colon, and here's another way to create a vector with the C function. So I'm just putting in the values true, false, false, true. And and assigning that via the assignment operator to a variable called b. I run that with Control Enter, and then I can print it out here. Okay, so this is a logical vector. I can see that by saying type of b. Logical vectors can take on two values, either true or false. Technically, there's a third value of missing, or NA, but think of it as a true-false vector. We've already seen integer vectors. That was A. So type of A will return integer. If you want to use C to create an integer vector, this actually won't work. So if I run this and I say type of D, that is a double precision floating point number. If you want to really force it to be an integer, this is technically not really all that important. You have to put L after them if you're using the C function to create them. So that will be integer. So 1L is the integer 1, and 1 is actually a double precision, which is the one we're doing next. So double precision, we'll talk more about this later in the course. This is a way of storing on a computer decimal valued numbers. So let's see a couple examples. We've already seen one like this. But you can also do, all kinds of things. So, like I said, decimal numbers. There's a special variable pi, which means what you think it means. And if you want to get the number e, use the exp function with exponent 1. So let's print e out. That's clearly these are not integers. And R stores them as double precision floating point numbers. Now these aren't used that often. There is a complex number system in R. So if I type I, that doesn't work because it thinks I is a variable, and it's looking for one and it can't find it because we haven't defined a variable called I. If you want the complex number I, you do 1I. And then if you do, well, let's do this. If you want to define, you could do it this way. Or you could omit the 0 because that doesn't add anything. And type of G is complex. And when is this used? Not that often. In my experience, if you do something like, if you've studied Fourier transforms, so if you do FFT of some set of numbers, 10 numbers, this returns complex numbers. And so, of course, if you type of that vector, you get complex. Okay, the last type we're going to talk about is character vectors. So we can create that with the C function. Print it out, you get this. Now, a surefire way to know that it's a character vector is when it gets printed out, it will have quotes around each element. But you can also check with type of. That will return character. This is different from, we'll see this in just a second. When we did the logical vector here, it just printed capital true, capital false without quotes around it. So that should be a tell that this is actually not a character vector. This is a logical vector. Now, as I alluded to earlier, R has special values to represent various different things. NA is used to represent missing values. Null is supposed to be a generic length 0 object. There's several purposes for this. There's also something called NaN for not a number. We'll see some examples of that. And there are infinite values, minus infinity and positive infinity. So let's look at some examples to see how these work. I'm going to define a vector here with a missing value. And if I run this and type it out, it just leaves NA in the second entry. So this is meant to represent, okay, there should have been data in that second element, but we don't have it for whatever reason. So it's like a placeholder for missing data. Now, if we do the same thing with null, null, something different happens. It basically just removes it. So you can think of null as a length 0 object. There's really no reason you would ever type this out. This is just trying to show you how it works. And we'll see further in the course, there's a couple other uses for null. One of them is to remove a column from a data frame. You can use null, assign null to it. Okay. Let's see. So R does have, let's call this B. R does have complex numbers. However, you have to explicitly tell it you want complex numbers. So if I tried to compute the square root of -1 here, we're not going to get a complex value. It'll say warning message in square root -1, NaN's produced. So if I print this out, it replaced square root -1 with NaN. So the square root function will not return a complex value. Actually, now I'm curious. Can you force it to return complex? You can give it complex arguments, but I think there's no additional argument to say you want it to convert to complex. So actually, let's check. So if we do square root -1, we get NaN. If we do square root 0 plus, let's see, -1, give it explicitly a complex number. That works. Okay. So you can force it, but you have to give it a complex number. If you give it a real number, a real negative number, it will give not a number. Okay. We also have infinites. So E is and infinite has the property if you try to like add something to it. So this will increment the first and the third elements, but infinite plus 1 is still infinite. Okay. Now there are functions in R for detecting these various special values. So if I do is.na of the first vector, let me rerun this. All right, that's A. Is.na of that vector. So it's applied to the entire vector, and it returns another vector. And you should be thinking right now, this is a logical vector. And basically, the first element of the return value is whether or not the first element of the input value is NA or missing. So that's false. The second one is NA, and the third is not. So that's why it's false, true, false. There's also one for is.nan. That's all false for A, but if we apply it to B, let me run this first. Apply it to B, you can probably guess what's going to happen. That's a null, but we could apply it to D. Is.nan of D, false, true, false. So the second, let me print out that's D. The second element of D is not a number, so is.nan of D returns false, true, false. There's also is.finite, which is a bit of a catch-all. So let's apply it to each one. So is.finite of A, it treats the NA as false. So just a reminder, that's A. So if you type is.finite of that vector, 3.7 is finite. NA is not finite, according to this function. And 7.2 is finite. Let's try is.finite of D. Same thing. It treats nans as not finite. Is.finite E. Same thing. Okay, so feel free to try these functions out, and also feel free to look at the help function. So question mark is.finite will tell you exactly what this function is supposed to be doing. And in general, in these videos, you'll probably be watching and wondering, oh, what would happen if he had instead typed is.nan of E? And I won't have typed in everything that you're wondering about, but you have the RStudio console up. You can type it in yourself. So that's the benefit of following along. You can get those kinds of questions, those curiosities answered immediately for yourself by just running them. So don't be afraid to type in code here that I'm not typing in if you're curious about something. I will always leave the finished product with all the code that I've typed in for you as well. So don't worry about making a mess of this version. Feel free to try things out. All right, now on to one of kind of interesting quirks of R, which is automatic coercion. So if you try to create a vector, an atomic vector, which has elements that are different types, remember the rule is that atomic vector, they all have to be the same type. So R is going to coerce all of the elements to be the same type. And the rule is it always coerces things to the highest type in that you give it in the vector, which implies that there's some kind of ordering to the types. So this is the ordering for R. Logical is the lowest type. Integer is the next lowest, then double, then complex, then character. So the way this is going to work is if I give it an integer and a logical in the same vector, it's going to convert everything to integers. All right, so let's see an example of that. A is going to be a logical vector. Now, even though A is length 1, it's still a vector. There's actually no scalar objects in R. Scalars are just vectors of length 1. So if I do type of A, this is a logical vector, logical atomic vector. Now if I try to create B as A and adding an integer to it, now this is the first time we've seen this syntax. You can actually, so in all our previous syntax we were giving individual values inside of C. Here we're giving a vector inside of C. All this is going to do is concatenate 0L to the end of A. But there's going to be a problem because 0L is integer type and A is logical type. So what R is going to do is it's going to convert everything to the highest type that's available in here, which is integer. So if I run this and I do B, it converted that true to a 1. So the rule, apparently the rule in R is it converts trues to 1. Let's try, actually let's change this. Let's make this true false just to show you how this works. So that's A. If B is this, it converted the true to 1 and the false to 0. All right, now let's keep going up the chain of types. So I'll define D as take B and add the number 1 to it. Now think for a second, what type is this? This is actually a double type because we're not putting the L at the end. It's the same thing as doing that. So if I do type of D, that is a double. And let's print it out. It still looks exactly the same, so you can't tell by looking at the vector that this is a double, because this one looks pretty much the same, and that's a integer type. Actually, we never did do that. So type of B is integer. Okay. All right, so if we do E is concatenate D with a complex number, it converts everything to complex. And if we do type of E, we get complex. And if we try to, let's do this. We'll concatenate E with the character string square root of -1. It's going to convert everything to character strings. And you can tell that a couple of different ways. One is that over here in the console it has quotes around them. And then, of course, you can always type of. Okay, so a few notes about this. Automatic coercion is often a source of silent bugs. So something, for example, something is happening here. The D part of this is getting converted to complex. It's a different type. But when I ran this piece of code, up here, it didn't print out any warning, like warning, elements are being converted to the higher. There's nothing that gets printed out. So this is what people call silent bugs. So if you did something like this is probably something you would never code up on purpose as something you intended to do. But there's no warning or error that gets printed out. And if you try to do math on this vector, you're going to have a bad time. So this is can be a problem, but R does this automatically, so it's just good to know that it does it. As I said before, R does not distinguish between scalar and length 1 vectors. For strings, you can use either single quote or double quote. Most people, just by convention, use double quote. Yeah, and those are some notes about that. Sometimes coercion can be useful. Let's see an example of that. So I'm going to create a logical vector, true, false, false. And if I wanted to count up the number of true values, I could do sum of that vector. Now, on its face, this doesn't really make sense, because what does it mean to add true to false? However, what's going to happen is the sum function will see that this is a logical vector, realize it can't do math on a logical vector, and so it will coerce to a higher type, integer type. Actually, I don't know if it's integer or double. We'll have to check that. And it will do the math on that. So the true will get converted to 1, and the falses will get converted to 0, and this will give 1. Now, what is the type? Integer. Okay, well, that answers that. Same thing for the mean function. So this should give 1/3. And of course, that's not an integer. That's a double. All right, what are some other things? Oh, nchar. So nchar is a handy little function that works on character strings. So, and it counts up the number of characters. So let me, oh, by the way, you can highlight and run parts of it. So what's happening is here, I don't want to run all this at once. I want to show you what this inside part is. So I'm going to highlight it, do Control Enter. That will run it. And what nchar is, it counts up the number of characters in a character string. But this is, of course, not a character vector. It's a double vector. So what it has to do is convert to character string first, and then it counts them up. So apparently, actually, let's do that explicitly. So let's do it this way. Let's just add something to the end. So this will cause coercion. And you can see how it gets coerced. So pi gets written down apparently to 14 decimal digits, and same for e. And these are given a shorter representation. So good to know. It doesn't add a bunch of zeros here to match the number of digits here. So that's automatic coercion. In R, you can also do manual coercion, which means that you as the programmer are explicitly doing the coercion yourself. This is often safer to do as a programmer. You don't want to generally rely on automatic coercion, but of course you get shorter code if you allow R to do it. So use automatic coercion with care. If you want to be really careful, use manual coercion, as we'll see here. So the functions all have this same kind of syntax, as dot, and you can see it gives a bunch of them. We're not going to look at all of these. So we'll start with as dot integer. So this will coerce to integer. We could do as dot, I'll just give you some examples here. That does what we did above. As dot double, this one's not too interesting because it gets printed out exactly the same, but if you needed to convert integers to double for some reason, it would do that. And you can also do as dot complex. So these are real numbers, but real numbers are a subset of the complex numbers, so it will print them out here as complex numbers. There's also a generic function called as, so let me just show you how that works. So if, for example, if you had this would be kind of an odd example, but if you had the types stored in a vector and you had to loop over them and do all the conversions, it wouldn't be convenient to have like a bunch of if statements and pick the correct one here. You can actually supply the type that you want to convert to as an argument to the as function. So let me just show you this, how this works. True, false, false. So if I want to convert this to a character vector, I give a second argument to say what I want to convert it to. And if I instead done double, it's going to give 1, 0, 0. And this is the first time we've seen this. So here, this is a different printout than this. You can see the difference is that when you convert it to character, it puts quotes around it. So the string true is different from the logical value true. And you can always look it up by doing type of on the vector to see what type it is. You can also tell by just seeing what gets printed out here. Okay, now vectors have certain properties. So let's create a test vector so we can look at these things. Okay, so B is the vector 1 through 10. That's what you think it is. There's various properties you can look up about vectors. So the one that's probably used most often is length. So length of B will give 10. You can also supply names to the elements of a vector. So let's make a shorter one called A. So there's A. If we do names of A, we get nothing. Well, we get null back. Remember, this is our generic length 0 object. So this is how R is representing the fact that the vector A, which is an integer vector, does not have names associated with its element. So it's giving you a null to tell you that. Now, you can set names using the names function. So let's see how to do that. So names of A. So that's A, 1, 2, 3. You can set A like this. So this is going to look a little bit strange, but let me explain what's happening here. Bill, Susan, Jamie. So that line, I've set the names property or attribute of the vector A to Bill, Susan, Jamie. And when I print out A now, it puts the name of each element above it in the printout. You can also do it this way. When you do the creation of the vector using the C function, you can say this. So that will do the same thing. Now, okay, let's go back to this. This should look a little bit weird because in all our other examples where we're using this assignment operator, we have an R object on the left-hand side. So let's look at some examples. So here, 1 to 10 is getting assigned to a variable B, and then we can look at the variable. Here, 1 to 3 is getting assigned to the variable A, and then we can look at the variable. So the left-hand side of the assignment operator is always some kind of R object. Now this is a bit weird because the left-hand side now is not an R object. It's like the return value for the names function with A as its argument. Okay, so this is a bit of an odd syntax. And when you do this, this is called using a replacement function. Not all functions are replacement functions, but the names function is. What that means is you can use this to replace the names property or the names attribute of the object A with this vector. And you can see that's exactly what happens. So before, when we do this before, there's no names attribute. When we do this assignment using the replacement function, now it does have them. So this syntax should look a little bit strange, but it's perfectly legal and often used R syntax. And this is called a replacement function. Let's actually look at the documentation. Okay, so how can you figure out if a function is a replacement function? It will, in its usage, it will have something that looks like this. So here they're telling you can use it on the left-hand side of an assignment operator. That's telling you that it's a replacement function. Now you can also use it, generally like this on the right-hand side. Let's see an example of that. Let's just names A is names of A. So here we're putting names of A on the right-hand side. This is Bill, Susan, Jamie. And then we're assigning it to a character vector called names A. So names is a function that can be used both on the left-hand side and the right-hand side. And you can see that in the help file. It tells you that. This also works for length. This is kind of interesting. So there's B. Let me get rid of this. Okay, there's B. Bill, Susan, Jamie. If I do length of B, I should get 3. That makes sense. Now if I try to do length B is 7, and then I type B, now it's basically saying, okay, it was 3 now, but the user has told me that it should be 7. I don't know what to put in those 4 other elements, so I'm just going to put NA in them. So that's what R does. So you actually can change the length of the vector using the length function as a replacement function. And you can see that it's a replacement function because it's on the left-hand side of the assignment. Okay. You can also remove names. So unname B will remove them. However, this is kind of interesting. You actually haven't removed them from B. B is still there. If you actually want to remove names from the object B, you have to say B is unname B. So here, unless an assignment is happening, nothing actually happens to the object B. This is just returning B without names. If you actually want to change the character of B, whether or not it has names, you have to actually assign it back to B. So if we do this and type B, you get that. Another way to do it is with as.vector. Let me reassign B to have names. B has names now. B has names. As.vector B will also remove them. All right, so something to do on your own. Look through the documentation for as.vector and is.vector and see exactly what those functions are returning. Now you've seen me use both this assignment operator, which is less than followed by hyphen, and now you've seen me use equal sign. So what the heck is the difference? Where'd you see? You saw me use equal sign here. So what the heck is the difference? So when you're assigning to a variable, you can actually use either one, either the assignment operator or the equal sign. Let me see an example here. So B is, let me just copy this. All right, so we know that works. That's B. This also works. So this is a valid assignment operator. So these two lines actually do exactly the same thing. But you can see that we're using, in this line, we're using equals in 2 different ways. We're using it to do the assignment of this vector to the variable B. And we're also using it to set the names attribute of the elements of the vector B. So which one should you use? I think it's good practice to always use the assignment operator when you're assigning an object to a variable. And then you have to use equal sign when you're naming arguments to a function. In this case, we're naming the names of the different elements of B. You actually can, this is kind of interesting, you actually can do this. This is weird. Nobody ever writes R code like this, but it doesn't throw an error. So we look at B. Nothing happened here aside from setting 0 to be the third element. It actually didn't assign the name Jamie to that element. What doesn't happen is it doesn't assign anything to a variable called Bill. So Bill's not found. Susan's not found. But Jamie is. Jamie is 0. because this actually did an assignment of 0 to Jamie. Now, nobody ever writes code like this for good reason, because this is very confusing. So it should be written like this. But you can actually use it there. So to keep things straight, most people recommend, and I recommend, use the assignment operator for assigning objects to variables instead of the equal sign here. That helps you at least keep things straight in terms of what the equal sign is used for in your code. It's used to assign arguments inside of function calls, and not to do assignment operator, do assignment of objects to variables. And let me set this back to assignment, just so you have that saved. Now, I don't recommend doing that, but I just want you to see the code. Okay. Another attribute, so you see names and length. Another attribute that you'll see is dim. So let's make a vector. A is the numbers, integers 1 through 8. If I do length of A, it's going to say 8. If I do dim of A, you might guess that this is going to say, okay, A is like an 8 by 1 vector or something like that. But it doesn't. It says null, which means that there's no dim attribute set for the A object. So one thing to understand is that a matrix in R is simply a vector with its dim attribute set to something. So let's see an example of that. So if we say dim is another example of a replacement function, meaning you can put it on the left-hand side. So if we say A's dimensions are 4, 2, then we can say dim A, and we'll print it out. So dim A is 4, 2, and print out A. Now it has changed A. All right, let's run through this one more time. So let's start from the top. A is the vector 1 to 8. That's what it looks like. I set its dim attribute to 4, 2. Now its dim attribute is 4, 2. And I print it out. Now it's a 4 by 2 matrix with the same numbers. It has the numbers 1 through 8. But now it's a different type of object. It's a matrix instead of a vector. We can also reshape it. So we could say dim A is 8, 1. And then print A out. Now it's a 8 by 1 vector. We can also remove the dim attribute by setting it to null. Here's our first example of something useful. Null is something null is used for. It's to remove the dim attribute of A. And then we print it out. Now it's back to a regular old vector. So it's not a matrix anymore. So the only thing separating a vector and a matrix is that its dim attribute is set to something. Now it has to be set to something that makes sense. So let's start over and let's do something that doesn't make sense at all. Dim A is 4 by 3. This gives an error. So the dims 4, 3, whose product is 12, do not match the length of the object, which is 8. So this doesn't work. It's still that. But this will work. So as long as the product of the dimensions matches the length of the vector, everything will work. Okay. Now, one thing to recognize is when we change the dimensions to be 4 by 2, that works. There's 4 times 2 is 8. We have 8 elements here. But R had a choice in how it was going to fill up this 4 by 2 matrix with the numbers 1 through 8. It could have gone like it did, 1, 2, 3, 4 down the first column, then 5, 6, 7, 8 down the second column, or It could have said 1, 2, 3, 4, 5, 6, 7, 8. It didn't do that. So by default, R uses something called column major ordering, which means you fill up, you take the first column, you fill it up, then you move to the next column, fill it up, so on and so forth. So that's a way to define a matrix in R. You could take a vector and set the dim attribute. It's actually not the most common way that matrices are defined in R, at least in R code that I've seen. Usually you use the matrix function. So let's take a look at the documentation for the matrix function. So here's the description. Matrix creates a matrix from a given set of values. As.matrix attempts to turn its argument into a matrix, and is.matrix is a test to see whether or not the object is a matrix. And here's how it's used. The first argument is data. So those are the numbers that you're going to put in there. The next two arguments are number of rows and number of columns. The third argument is by row. So this is going to say, now the default value is false. So if you don't specify by row, it's going to default to false, which means it's going to go by column or column major ordering. And then you can also specify dim names, which we'll talk about, if not in this video, in the next one. Let's see. Yep, and this explains what those arguments do. Okay, so let's see this in action. I'll define a matrix M, matrix 1 to 8, n row equals 1, n col equals 1. All right, so I'm going to actually say data here. Oh, and that doesn't work. We should say 4 and 2. All right, so that's good to know. Matrix data 1 through 8, n row 1, n col 1. We got a warning. In matrix, blah, 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 data length differs from size of the matrix. 8 is not equal to 1 by 1. So what did it actually give? It probably just gave a 1 by 1 matrix with the first element of the data. So R kind of detected here that this isn't what I intended to do. So it gave me a warning. It still ran the code and assigned something to M, but it gave me a warning to say, hey, this probably isn't what you wanted to do. So maybe take a look at it. And we took a look at it and said, yep, that's right. We really wanted 4 rows and 2 columns. So if I run that, that gives that. So one thing we did here in this call to the matrix function is we specified its arguments by matching, let's go back here, the value, so 1 to 8, to a name of the argument. And those match the names here, data, n row, n col. N row is 4, n col is 2. Now, you can skip that. You can remove these. And this will work. But the question is, how does it know that 1 to 8 should get assigned to data, 4 should get assigned to n row, and 2 should get assigned to n col? The rule is that it just goes in order, which is what you'd expect. Now you can get weird things. So if you can do these out of order if you name them. So n col, if I say n col equals 4 and row equals 2, we're going to get a 2 by 4 matrix. Okay, so that's fine. You can specify them out of order, but you have to name them. Weird things happen if you specify things. Okay, let's do something weird. We'll say 2 columns, 4 rows, and right here I'm going to put true. Okay, so I think I know what's going to happen here. It's going to assign this first one to data. That has to be n col. This one, not sure, so let's skip it. This one is obviously goes to n row, and I think it will assign this to by row. So let's see. Yes, so this did row major ordering, 1, 2, 3, 4, 5, 6, 7, 8. Now I don't recommend writing R code like this. This is very strange syntax. You're giving the arguments out of order, and then one of them, for some reason, or two of them, are not named. So don't write R code like this. I would just say, to be more explicit, well, first I would do them in order. So that's much better R code. So the lesson here is there's often different ways to write the same piece of code, and they're not all equal. You want to write code that's going to be easy for you to understand and easy for other people to understand as well. If I had left true in here without naming it, now I have to use a bunch of mental energy to figure out remember what the rules are in R for how it assigns arguments when they're given out of order and some of them are not named. And then I also have to go in and look at the matrix documentation to figure out, okay, what actually is that true going to get assigned to. So there are good and bad ways to write R code, and even if they give the same result, some are better than others. Okay. There is, you can also give names to matrices, but now you have a two types of names. You can give column names and row names. So let's look at M, and let's say 4 rows, 2 columns. There's M. I can set call names of M. This is another example of a replacement function. And these aren't very informative names, but just so we have something to put in there. Now if we do that, it names the columns. That's great. But it replaces the column names with this square bracket 1, square bracket 2 here. We'll learn more about square brackets in the next module. We can also set row names. Here I'll define them a little different. This assigns row names. You can also extract them, call names M, row names M. That way. So call names and row names are examples of replacement function that can be used both on the left-hand side and the right-hand side of the assignment operator. All right, we've already seen the function type of, which gives us information about what the underlying type of object is in the vector. There's also a function called class. So if we do, let's look at, class of M. This returns matrix array. Let's see, if we do class of just some vector, that returns integer. So that's a bit strange. If you, I said that a matrix is simply a vector with a dim attribute. So if I do class of that, it gives matrix array. But if I hadn't set the dim attribute and just take class of that, it gives the storage type. So really it should say like vector or something like that, but it doesn't. It says integer. It gives the storage type. But forget about that for a second. Class M is matrix array. That implies that maybe there's some other type of object called an array, and that's true. So an array is a matrix-like object in that it has multiple dimensions, but it could have more than 2 dimensions, where a matrix is really just a 2-dimensional object. Okay, so let's see some examples of how this works. So let's look at M. That's that matrix. And let's reset the dimensions. Dim M, instead of giving two numbers, actually let's look at what dim is. That's 4, 2. There's two numbers there because a matrix is a two-dimensional object. If we set it to something like this, give it 3 numbers, and then print it out. Oh, now we get something strange. So this is telling us that basically this is two matrices like put together, front and back. And so this is telling us this is the first like slice of that array. That the first slice is a two-dimensional object. The second slice is also a two-dimensional object, and these things are the same size, meaning you can like put them together. Okay, so R does have support for higher dimensional objects beyond 1 and 2 dimension. Don't get used that often, but there are some use cases. Okay. Now, another important concept, we talked about automatic coercion. This is often a source for silent bugs. Another source for silent bugs is something called recycling. So let me show you how that works. It's a same thing as automatic coercion. It's very useful, but it can also be slightly dangerous. Okay, let's look at this. So I'm going to make a matrix. I'm going to give it the data 1 through 3, but I'm going to give it more than dimensions that imply an object of more than 3 things. So I'm going to say 3 rows and 4 columns. So R is going to have to make a decision about what to do here. And what it does is it takes that data 1 through 3 and it just recycles it to fill out the matrix. So by default it does column major ordering. So it does 1, 2, 3. Starts back at the beginning, 1, 2, 3, 1, 2, 3, 1, 2, 3. If we had instead done this, let me give you another tip for learning and building your intuition. One thing you should try doing is type out the code and pause the video and then try to guess what it's going to give. So I'll do I'll just stop for a second here. Try to guess what this is going to return. Think about that for a minute. Now in theory, what it should do is it should create a 4 by 3 matrix, and it should use the data 1, 2, 3 to fill in that matrix. And it should do it in column major order. So when it goes down the first column, there's 4 rows. So it should do 1, 2, 3 in the first column, and it should start back over in the last element with a 1. Maybe that's a bit too much to think about in our head. So we'll just show what it looks like. So it does 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it did recycle the values 1 through 3, and it did do it in column major order. So this is exactly what it should be doing. Now these both work, but sometimes it won't work. So let's do this. 1 through 5, 4 rows, 3 columns. Again, sorry, 1 through 5. Again, try to guess what's going to happen here. Okay, it worked. It gave us something here, this thing. But it also printed out a warning. Let's read the warning first. In matrix 1 through 5, 4, 3, the data length, which is 5, is not a submultiple or a multiple of the number of rows. Okay, so it detected that if you were to recycle 1 through 5 to fill in this matrix, it's not going to end at the last element. And you see here, it ends at 2. So it did 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 1, 2. And R is smart enough to know that maybe you didn't intend to do that. So it gives you a warning message. Now, it doesn't give an error. It still runs. but it does give you a warning that probably you didn't intend to do that. Now, the most common way that recycling gets used with the matrix function is to specify a default value. So if I say matrix NA for 3, remember that this is a vector of length 1. It's a missing value. But it's still a vector. So R can perform recycling on this. And it's only one thing, so it gets recycled immediately when you go to the next element. So this is a way to fill in a 4x3 matrix with a default value NA without having to do, for example, we haven't seen that yet, but you could do a length 12 thing here. So this would give NAs, we'll see rep in a later lecture, but this will give 12 NAs. And so this should work exactly like you expect. But that's a longer code. This is nicer because it's shorter, and it uses recycling to do it. So this is what I mean when I say that recycling is really useful. This is nice, easy to read code, and it uses recycling to reuse the value NA to fill up these 12 entries. But it's good to know that this is what's happening, and it can be a source of silent bugs. So maybe, for example, here you intended to give it a data of length 12, but you only gave it a length 3. And just by accident, the number of elements of that matrix, 12, is a multiple of 3, so it fills it up. And maybe that's not what you intended to do. So what I recommend is try not to do this very often, because this is hard to wrap your head around sometimes. You could do this. This is fine. This is easy to read. The number of elements of a matrix will always be a multiple of 1. So this will always work, and it's not too confusing. Okay, this is just a note that exercises this week, we're going to look at some other vector types, namely factors and dates. So that will be coming. Last thing I want to talk about are generic attributes. So for any R object, you can set sort of custom attributes. For a vector, something like length, I'm not considering that a custom attribute because that's something that's very specific to vectors. They're always going to have a length attribute. Let me show you what I mean by this. So M matrix 1, 8, 4, 2. So here's a matrix. And I should be using my keyboard shortcuts to go back and forth. 2 goes to the console, 1 goes back to the source code. If I type attributes of M, we get a dim attribute. So the object M has an attribute called dim, and its value is 4, 2. So signify that this is a 4x2 matrix. If you want to set custom attributes, you can set them with the attr function. This works both on custom attributes and attributes that are already there. So I could do this. If I wanted to change the dimensions of M to be a 1x8 matrix instead of 4x2, that will do it. You can also set what I've been calling custom attributes. So, I don't know, color of M, if matrices have colors. Oh, this is a cool feature of RStudio. If you type in a recognized color, it will actually color the text. And then if I type, let's give one more, the weight of M, and then I do attributes, that will give, in addition to the dim attribute, you can give the other custom attributes for the object. So this not only works for matrices, it works for any R object. There's lots of use cases for this. I don't use it that much, but it's good to know that you can do this as well. Okay, that's it for atomic vectors. The next one up, we're going to look at lists, which are non-atomic vectors. They're more generic data structures.